So when TypeScript was first announced many years ago, I recall thinking to myself, I really don't want to write my UIs in Java. And at the time, when I heard about TypeScript, I thought, this seems like a really bad idea. But it turns out I had a very distinct misunderstanding about what type systems are. I spent way too many hours going down the rabbit hole researching type theory for this talk. But I've distilled it down, and I want to share with you how type systems and functional programming ideas can help you write better code. There is code and math in this talk, so please be warned. But I will try my best to avoid jargon. So can I get a quick show of hands? How many of you have shipped a bug into production ever? I'd be surprised if not everyone is raising their hands. And I know I have, right? And it's okay. We're human. Programming is hard, and it's really easy to add bugs into software, especially in the Wild West that is JavaScript. And my journey begins with a bug, as with many programming journeys. And I don't know about you, but when bugs inevitably happen, I feel pretty terrible about it. And I experience a real crisis of confidence, especially if you cannot figure out why the bug is happening. But when you do figure it out, all is good in the world, and your confidence is restored. Hopefully this graph isn't too unfamiliar to most of you. Now, I've been programming for a while now, and I've seen my fair share of JavaScript errors. And after the millionth time seeing undefined is not a function, I thought to myself, there has to be a better way. Swipe left. And whether you prefer TypeScript or Flow, and the many other typed options for JavaScript like Reason, PureScript, Elm, etc., there is a little something for you in this talk. So, what is a type system other than something that yells at you a lot? And there are many different definitions for this, and later this evening we'll hear from Anders himself, who is the creator of TypeScript, about how its type system came to be. But my explanation is a type system is really a way to add constraints to your code. And the type system is there to help you enforce logic that is consistent within those constraints. But why? Why are constraints useful in your code? So here's my bold claim. Constraints are good because they limit the number of bugs in your program. So let me explain with an example. Here we have a simple function. It takes one argument and divides it by 2. So how many ways can this function fail? I came up with some possible inputs that I could pass into this function, and here we have our usual suspects like null, undefined, numbers, strings, and so on. And now I'm going to enumerate over all of those inputs. After running this, we should see an array of test results. So let's run this in our console and see what happens. Unfortunately for us, null and undefined don't have any methods defined on them. Wouldn't it be nice if the compiler could tell me that, though? I don't want to have to wait to run my code in the browser every time in order to find these bugs manually, or to have to write a million unit tests because I'm pretty lazy. And this is only a simple function, right? It's division by 2. Now, in JavaScript, your first instinct might be to add checks for null or undefined. Or if you want to get extreme, don't use this in production, you can even define undefined as a function, so you'll never see that error ever again. But you end up having very defensive code, and you're checking argument types at runtime, so you're shipping a lot of code to the browser that you don't really need to. Which is fine, I guess, but I know it can be very frustrating not catching these kind of simple bugs before you ship into production. So anyway, if we fix the errors and we run our test again, we'll see that most of these inputs throw type errors or result in some kind of nonsensical value like not a number. So let me ask you again, how many ways can that simple function fail? Think about all the possible inputs that you could pass into this function, every single one of them. There is an infinite number of permutations of garbage you could pass into this function. You could give it an array of 11 ones, like 1, 2, 3, 4, it doesn't matter. 100,000 character string, these would all cause problems. But using TypeScript, let's just add a very simple type annotation to drastically constrain this function down to only accepting one set of types. So now x can only be a number, and the compiler will yell at me if I pass in anything else. If you try running this function with every single number possible, none of them should cause an error, at least at compile time, and assuming you have typed your program correctly. So my bold claim for today is that types and constraints will reduce the bugs in your programs. And it turns out that there is a lot of things that functional programming can teach us. Type systems are grounded in mathematics, so is functional programming. And very interestingly, type systems can also be applied to object-oriented languages. It's not unique to a functional language. And I think the concepts behind this are very interesting. And understanding it can help us understand why type systems help us write better code. So let's start with a quick high-level overview. Functional programming is the practical implementation of a bunch of mathematical theories. We have proof theory, which is about constructive logic and mathematical proofs. We have category theory, which is about algebra. It's about how things compose. It's about abstractions. And if you've ever dealt with something like a monoid or a functor or a monad, these are all examples of categories within category theory. And finally, we have type theory, which is about programs and the idea that propositions are types. So Curry, Howard, and Lambeck are logicians and mathematicians who independently found that these three theories were describing the same idea, just in different ways. And so the correspondence between them is really the relationship between these three theories: proof theory, category theory, and type theory. Now, if this sounds arcane to you, don't worry. I'm going to try my best to explain. The key takeaway I want you to have are these two ideas. The first being the idea that propositions are types. For example, here, my type signature states that given that two numbers exist, a number also exists. And the idea that programs are proofs of those propositions. Because just like in real life, you don't just get to say that something is true. You have to prove it. You have to show your work. And here, x plus y produces a proof that we have a number, that a number exists. So we're going to revisit that definition again later to see why it's useful. But now let's take a look at functions not in the programming sense, but in the mathematical perspective. So this is a function in mathematics. In plain English, it maps an object of type A to an object of type B. Pure functions, if you know what they are really mappings. For a given input, you get an output in return, and you always get the same output. Remember what we said earlier. Types are propositions. They assert that something is true, or something exists. For example, this function will return a number. And our programs are proofs. A number exists because here in my code, I have produced the number 1. Type checking is therefore proof checking. And if you work backwards from that intuition, what this means is that if you write good types, you can often let the type system suggest the implementation, basically almost like type-driven development. And in theory, you could declare all of your types and function type signatures without writing any actual code. And if it compiles, your program should just work, trademark. Then it's really a matter of filling in the details, right? It's proving that these propositions that you've defined hold true. So here's a simple, concrete example. This function takes a list of items and returns the first one. Once you've written the type signature, the implementation can sometimes seem very obvious. For example, if you try returning the list itself, you see a TypeScript compile error because we're not returning the right type. We're returning an array instead of a single item. So there's really nothing much else we can do here except to return the first item in the list. But you might notice that you could actually return any index in this list, right? Not just the first one, and this would still type check. And here we actually have an example of a limitation of type systems in that you cannot actually check that you're returning the first item in this list. Other languages with more advanced type systems may be possible with things like dependent types. But what I really want to highlight here is that TypeScript is not a silver bullet. It's really a pragmatic way to balance productivity and type safety. So let's go back and revisit the implications of the Curry-Howard-Lambeck correspondence, the meeting of proof theory, category theory, and type theory, and learn how it can help us write better functions. So here we have a graph of the function f of x is equals to x squared. What I want to call out here is that the pure functions in JavaScript are similar, if not the same, as the functions that you learned in high school mathematics. Pure functions, as I explained earlier, map an input to an output. So when you talk about pure functions, you also talk about domains and codomains. And the domain of a function is really the set of all possible inputs into that function. So for this function here, it's all the numbers. And the codomain of a function is the set of all possible outputs, which in this case is also numbers. Now, to improve the quality of your programs and the code you write, there is a notion of totality in the functions that you create. We know that functions can be pure or impure, but that is really independent of whether they are total or partial. A partial function is a function that is not defined for all possible input values. So think about functions that don't always return a value or return undefined. For example, this could throw an exception, it could be an infinite loop, or it could even crash the whole system. So let's look at the have function again. Clearly, this is a pure function. It doesn't have any side effects because it returns, it doesn't have any side effects, and it also returns the same output for a given input. However, it is a partial function because as we saw earlier, there are some inputs that could cause this function to throw an error. So let's look at all the possible domains and the codomains for this function. We know that if we pass it a number, it will give us back a number. If we pass this function a string, it could either return a number or not a number. And that's actually a feature, not a bug. JavaScript was designed to work in the worst of environments, and it will try its hardest to run your code no matter how terrible it is. It's going to try its hardest to make sure your application works. And of course, you also have your other types that you're familiar with, like null, undefined, objects, and arrays, which all return not a number in this function. And by the way, not a number is a number. Thanks, JavaScript. And finally, if you pass in a symbol, you get a type error, which is not actually an output or a codomain, it's an exception. Again, with a type annotation, we restrict the domain to only numbers, and therefore this function is total, at least at compile time, and it should never be undefined or throw an exception. But what is a total function? The total function is a function that is defined for all possible values of its input. So it always terminates and it always returns a value, never undefined or exceptions. So let's look at another function here. Fetch user takes a username as a string. It hits some API in the background and returns a promise. And this is a partial function because the fetch could fail and throw an error. So I'd like to introduce you to something to make this function total. The promise now resolves with a user wrapped in an either type. So this function can only return a promise that resolves to this either type. And whether or not it fails, you will always return this type. The either type encodes the two possible outcomes of this code. It returns a left, which represents failure, or a right, which represents success. So what we have here is actually a monad, but I promised no jargon, so don't worry about what that means yet. The idea here is that regardless of what you get back as an output, you want to return something with a similar interface so you don't have to care if it was successful or if it was a failure. Here we have an example implementation or proof of this type signature. First, I'm going to fetch a user from my API. Then I'll return a left representing failure if the fetch is not a 200 OK. Where I'm also going to pass in an error object, which we can use later, and note that this error is not thrown. If the fetch was successful, we return a right, in this case, an object that matches the user interface that I've defined in my application. When we use this function, note that whether or not the request fails, the return value has methods that you can call safely. So this code on screen won't cause any issues even if the fetch fails. When you get into functional programming, you'll learn how to compose these things to do more cool things. So look up category theory if you're interested in going down that rabbit hole. It's a very deep rabbit hole. The cool thing about the either type is that you can capture the failure and do something with it. For example, maybe I could alert the user and let them know with an on-screen message that something went wrong. Let's look at one more example. This function detects the first element in the viewport inside of a scrollable container element. Because this function can return undefined, it is also a partial function. For example, what if I pass in a selector that yields no elements? We can reduce the codomain of this function to make this a total function. By wrapping this in an option type, now every input to the function will give us an output in this singular codomain, and the return value will never be undefined. The option type and the either type are really quite similar. The main difference is that the either type also captures the failure value while the option type does not. So the option type or the option monad really represents some value or nothing. So this is the actual function implementation, but don't pay too much attention to it. You can see that there are two places where we can be undefined. Query selector will give you an undefined return value if it finds nothing, and array.find will also return undefined if it finds nothing. And unlike the either type, we don't care about the reason for failure here. We just want to return the value none. And if we do find something in the DOM, we'll return that element. So when we use this function, we get back an option type, which again returns a consistent interface regardless whether it is something or nothing. And both of these objects, something and some and none, have the map function defined. So my code is not going to throw an error like undefined is not a function. I mentioned earlier that domains and codomains describe the set of all inputs and outputs. So when you talk about sets, you're really talking about set theory. And in set theory, cardinality means the number of elements of the set. I made a bold claim earlier that the more specific your types and the more constraints you have, the less likely you will have bugs. This is not a silver bullet by any means, but lower cardinality does mean constraining the number of possible inputs in the function's domain. Now, I'm from Australia originally, so the analogy here is like kind of having a friendly spider in your code base. It's not going to catch all the bugs, but it will sure as heck eat a few. So let's start with the basics. A set is informally a collection of objects, and in our context, we want to think about the set of all values that we're dealing with. Here we have a type called conferences. Note that the type of this type is not a string, which would match every possible string. And because there are only 3 possible values, we say that the cardinality of the conferences type is 3. But if the conferences type was a string, then there could be an infinite amount of strings that would match this type. So what I mean by this is that primitive types are often not precise. And if you look at the cardinality of all of the primitive types that you have available in JavaScript, the only types with finite cardinality are booleans, nulls, and undefineds. And you probably don't want to write your application using just those types, unless you're really hardcore. Even the non-primitive type object has an infinite cardinality, and any possible object that you could define would match this type. And really what I want to say here is that defining precise types can help you reduce the bugs in your code. So let's look at an example. Here we have a generic function toString, which calls the toString method on the object that's passed into it. Even though null and undefined don't have toString defined on them, as we saw earlier, this will type check. And this is actually pretty alarming because you've lost type safety. And this will cause a type error if you try to run this code in your application. So now this is a function with unbounded polymorphism, which means that the type variable t can be literally any type. And you almost always want to stay away from the any type, right? It's not precise. And because we know that null and undefined are going to give us type errors, we want to make this a more bounded generic function. To do this, we add a constraint to our generic type. Non-nullable is not actually code, but it is a type as well that will constrain that generic type variable t for you. It tells TypeScript to exclude nulls and undefineds from that type variable. And now, assuming that everything else has toString defined on it, we have made this function total, since it will always return for every possible input. To put this visually, imagine a Venn diagram with 2 sets. One is the set of nullable types, in other words, null and undefined, and the other is the set of all types. And what you really want is the difference, right? You want all of the types minus the nullable types, and that leaves you with the non-nullable types. The non-nullable type is implemented with conditional types, which is a relatively new feature in TypeScript 2.8. And this is really the basis for many of the new helper types that they've just added. TypeScript ships with a number of these built-in types now, so they're very useful when you're thinking about constraints to your code. We've talked a lot about functions and functional programming concepts, but really the biggest takeaway that I want you all to have is that ultimately we should all be pragmatic. JavaScript is a multi-paradigm language. You can do object-oriented, you can do functional programming, you can do functional reactive programming, but You don't have to be too religious about it. And that's the same in terms of TypeScript and many of the other type languages, right? It's really that balance between productivity and type safety. You don't have to go all in order to benefit from it. You don't have to get a PhD in math either. And these tools will not solve all of your bugs, but you should be able to catch the obvious ones before your users do. And remember, take care of that spider in your code base. And remember that these three things. In the Curry-Howard-Lambert correspondence, propositions are types, programs are proofs of those propositions, and type checking is really the same as proof checking. Thank you all so much for listening. You've been great.